Our first order of business is to describe the normal form for an equation of a line in R2. So I have here a drawing in GeoGebra. We have our line L, and we have what's called a normal vector n here. The important thing is that this normal vector n is orthogonal or perpendicular to the line L. Here is a point x on this line. My goal is to find an equation which gives a condition for when x is on the line. So to do that, I'm going to add some stuff to this diagram. So you'll see here, I've added a point P over here. And I've added the vector which goes from P to x. The important thing to notice here is that this normal vector n is orthogonal to the vector x minus p. And it's always orthogonal when x is on my line. However, if I detach the point from the line, so if x is not on the line, then you'll see that the angle between x minus p and n is no longer 90 degrees. So therefore, I conclude that I can describe my line as the set of all points, or in this case, in terms of vectors, x, whose vector from p to x is orthogonal to n. That's what this equation here says. And this is called the normal form of the equation of a line in 2D. That 2D is going to become very important because it is not true in R3. We just saw the normal form for an equation of a line in R2. And we wrote it as n dotted with x minus p equals 0. And here, p is just some base point. Base point. Any point on your line will work. We can expand this expression out to get what's called the general form. So if we write n equal to ab and call c n dotted with p, then this becomes, well, first I get n dotted with x equals n dotted with p, and this becomes ax plus by equals c. And this is called the general form. Of an equation of a line in R2. I'm now going to talk about the vector and parametric forms of the equation for the line in R2. So I have it written over here. To understand what's going on in this equation, let's take a look at what I've drawn here. So over here, just as with the other diagram, I have my vector x, which goes to my point x. I have a base point p and a vector which goes to that base point. And the difference here is that now I have, instead of a normal vector, I have what's called a direction vector d. So the way that we're describing this is by t over here. This is the multiple of d, which will give us this vector x minus p. So right now, with what I have currently, t is 3.94. But as I move around, t changes from being negative over here to being positive over here. But the important thing is that x minus p runs through all multiples, positive or negative, of this direction vector d. Just as with the normal form of the line, we can expand out in terms of components the vector form of the line, and this will give us the parametric form. So remember, our vector form was x equals p plus t times d. So to get the parametric form, we can write p out as, say, p equals b1, b2, how about, and d equals, how about, a1, a2. And then our vector form, when we expand everything out, we get x equals, write it as a1 times t plus b1, and y equals a2 times t plus b2. And this is our parametric form of the equation for a line in R2.